say, and roll them.
And roll them.
Okay, welcome to section 1.4, an introduction to functions and pre-calculus. We're going to discuss today the graphs of a function and the difference between a relation and a function. A function can be a relation, like a square is a rectangle, but a relation isn't necessarily a function, like a rectangle isn't necessarily a square. Here's a relation. I equals 500R. It describes the relation between the amount of interest earned in a year and the interest rate R. In mathematics, relations are represented by sets of ordered pairs. None of this is new, it's just different language that we learn now. So a function, the thing that makes it unique, is that it goes from A to B in such a way that every element, every x in the set A is only used once as a y in the set B. That sounds very confusing, but look at it this way. For every member of the domain of f of x, there is one and only one member of the range. For every x, there is one and only one y. That's what makes it a function. If we had another line here from this x to this one, it would no longer be a function, because this input would have two different possible outputs. So if this was the case, this would be a relation, but it would not be a function. Again, each x goes to one and only one, y. The domain is the set of all the possible x's, and the range is the set of all possible y's. To determine whether it's a function, we get these sets, and you'll have homework problems that look just like this, 1 through 15, I believe. We look at the x values. Are any of them repeated? No. Every x value here is different. So obviously we're only going to have one value for y with each of those x's. This is a function. In the next one here, we see -1, 1. We also see -1, -1. Immediately we know that this is not a function, because this member of the domain, this x value, has two y values associated with it. And so therefore it is not a function. Remember, you have pause, fast forward, rewind, slow motion controls. If I'm going too fast, please use them. I'm just trying to keep the video as short as I can. So the symbol f of x, they say, is read the value of f at x. I've never read it that way. I read it f of x, or I simply say a function of x, simply as f of x, f of x. It's a function of x. F of x is just y. You've done functions all your life, just that you called them equations. Now, instead of writing y equals 3x plus 2, and calling it a linear equation, we would write f of x equals 3x plus 2, and we'll call it a linear function. A linear function. Again, the language is new perhaps, but the concepts aren't. The domain elements x can be thought of as the inputs. The inputs. You put in the x and you get out the y's. You get out the function of x. It's kind of like a candy machine. You put in coins, you get out candy. The domain is the set of inputs, and the range is the set of outputs. To evaluate f of x at some point, simply going to write out this equation, and the way I would do this is I would write f of equals minus f of, if I have to evaluate this at 3 different places, I'm going to do this 3 different times. And you see it doesn't take a lot of time when you're doing this over and over and over again. Okay, and then you can put in your 3 different values. Here, we're simply doing f of negative 2. So we'll put negative 2 in here. Very important, negative 2 is in these parentheses when you square it, because negative 2 squared is positive 4. But negative 2 squared is negative 4. So those parentheses are very important. And we evaluate and we simplify, and we get f of negative 2 is equal to 9. That's simply a point. That's the point, negative 2 comma 9. Before, we would have made a table of x and y values. Now we're doing the function of x. It's, again, the same math that you're using, different language. Now we're going to evaluate f of x equals 4x minus x squared at x plus 2. That simply means we're going to put x plus 2 in instead of x. So we copy down our function, we insert x plus 2 where x was, and then we evaluate and simplify. We expand this, remember FOIL or your shortcut methods for multiplying binomials, and then we just continue to simplify until we can't simplify it anymore, and we find that f of x plus 2 would be 4 minus x squared. Again, the domain is the set of all real numbers that make sense in the function. For example, if we were looking for the domain of this linear function, we're looking for all the possible x's, all the values that x could be. And in this case, x could be any number. There's no limitations. There's no mathematical reason why some number wouldn't work in this equation. So here the domain is all real numbers. And when you're writing this on your homework, we put a big R with 2 lines here. This stands for all real numbers. What time are we on?
8 minutes and 20 seconds.
Great. So now if we look at this one and we're trying to find the domain, we have to think logically, what values of x don't make sense? See, the domain is going to be, the answer is going to be all the x's that work, but very often it's easier to name that by the x's that don't work. So here's a square root. We know that you cannot take the square root of a negative number. So we look for what would make the value in here negative. What would make x minus 3 a negative number? And those are going to be the values that don't work. When we solve this, we see that x has to be greater than or equal to 3. If we put 2 in here, 2 minus 3 is negative 1. You can't take the square root of negative 1, so negative 1 is not a member of the domain. And so the way we would write this in set notation would be x such that x is greater than or equal to 3. This is called set notation. These funny little bracket thingies here describe a set. Find the domain of the function x plus 2 over x squared minus 1. Well, again, we think what value of x is not going to work mathematically. And since we know that you can't have a 0 in the denominator, we have to look for the values of x that would turn that into 0. And then we know what can't be in the domain. So we set x squared minus 1 equal to 0. We solve. And we find that the denominator becomes 0 when x is positive or negative 1. And so our domain is the set of all x such that x does not equal positive or negative 1. You see, it's easier to list what x isn't than what it is, very often. Anyway, that's the end of part 1.